Okay, so let's get started. So last time, I would say that I have talked about the most important component of this chapter. Okay, so based on this example on three springs, two mass system, right? So I talk about how to set up the equations of motion, right? So for the two particles, and then I also talk about how to solve, right? So this system of differential equations, and in particular, right? So I introduced the concept of this eigenfrequencies and normal mode, right? And this would be the very important concept, right? So in this chapter, okay. And then we also now know that the general solutions, right? So for the motions of the two particles, right? So can be written as a linear combination of the two normal modes, right? So that's very important. So, and then furthermore, right? So I talk about how do we solve the initial value problem, right? So now that we know the general solution is written as a linear combination of these two normal modes, right? So, but given some particular initial condition, okay, so what its motion would be, right? So will it be more oscillate in normal mode number one, or will it oscillate in the normal mode number two, or will it be a superposition of the two, right? So, and that we talk about that, right? And here, I would like to give you one example, okay, so where the systems is oscillate in a superposition of both normal modes. Okay, so it's right over here. Okay, so again, so the system that we are considering is the same two mass three spring system, right? So I'm considering this one. Okay, and in this case, I give you some real numerical values here. Okay, so this one should be K12. Okay, so this is K, this is also K, this is K12, and this is M, right? And now, with all the K and the M value set, right? So I also give you the initial position and the initial velocities of the two masses. Okay, so and the initial condition is that I'm going to displace this mass. Okay, so to the right by some amount. Right, so this is the equilibrium position. So I'm going to push this one to the right by some distance. I call one unit of distance over here. Right, so and then this one is keep fixed. Okay, initially, and then initially, right, so both masses are not moving, right? So I'm just keeping this one fixed, and then I drag this one to the right by 1 unit. So that's what I'm doing. And then now I release my hands and then let them move, right? And what happened immediately, you could imagine, is that of course this mass now will tend to move back to the left, right? So but at the same time, right, so this one will start moving to the right. So now you can see that I'm drawing this plot here, right? So where I'm plotting the displacement of the two particles as a function of time. Okay, so x1 is for the particle on the left, right? So this one would be x1, and then the yellow one would be x2. Okay, the yellow orange one will be x2. Okay, I'm sorry, I think I messed up. So the other way around. Sorry, the other way around. The yellow one is x1. The blue one is the x2. Right. This would be x1. This would be x2. So look at what happened to them individually. Okay. So for x1, so I'm just focusing at this curve over here. You can see that. So let me also clarify that. So this is the line of 0, okay, for this curve. And then for this curve, right, so this is the line of 0. Okay, so it's really, it's two, there are two sections in the same plot, okay. So if I look at this x1, okay, so and initially, x1 is at 0, right? So that makes sense, right? Because initially we are not giving it any displacement, right? So, but as time evolves, you can see that it starts oscillate, and then the amplitude of the oscillation increasing, right? So the amplitude of the oscillation increase over time. And at this point, right? So the amplitude of the oscillation is at maximum. On the other hand, we look at x2. So what happened is that initially, as the displacement over here, right? So that's the initial displacement that we gave. And then it will oscillate. But you can see that the oscillation amplitude actually decreased as a function of time. And then at this point, the oscillation amplitude is 0. Right? So then physically, what's happening is that you could really see is that initially this one has a larger oscillation amplitude, and that means it has more energy, right? As time evolves, the oscillation amplitude is decreasing because some work, okay, is being done to the other mass, right? So to make it start moving, right? So that is as a function of time, right? So the energy of this mass decreases, and on the other hand, the energy of this mass increases, right? So you can see, right? So this is small and small amplitude. That means that it has a small and small energy, right? So, and then this one, right? So increasing amplitude, that means its energy is increasing. Right? So and everything makes sense, right? So because the total energy is the total energy, right? So the total energy has to be the same and anyway. Right? So, okay, so but here we are not really trying to calculate the energy. You could try to do that, but you get the idea, right? So now basically at this point, so everything is reversed, right? So now the x2 is essentially not moving, and then the one on the left is moving at a large amplitude. Right? So and then if you keep tracing the time, right? So now the amplitude of the mass on the left decrease again, right? So and then now the amplitude of the mass on the right increase again, right? So that is now the energy, right? So of this one becomes weaker and weaker one more time, right? So now the energy on the right increase again. Right? So then it just happens again and again. So in this case, you could clearly see that we are not at a particular normal mode, right? So we are neither in the symmetric mode or the anti-symmetric mode. right? So because in the symmetric mode, you may still remember that the movement would look like this, right? So that is if you have the symmetric mode, right? So and if you plot the displacement of the two particles, right? So what you really get should be two identical curves overlay each other, right? So you should get a curve that looks like this, right? So if I have this x1 and this x2, right? So on the other hand, right? So if you have this anti-symmetric mode, and if you plot the displacement of the two particles, right? So you should get something like this, right? So if one looks like this, right? So then the other looks like this, right? So but here clearly it doesn't look anything like in either of the cases, right? So and that means, right? So this whole system is in a superposition of the two normal modes. Okay, that's what's happening. So, however, if we look at the graph on the right, okay, so what I'm plotting here is not x1 and x2 anymore. Instead, I'm plotting u1 and u2. So what is u1 and what is u2? So remember the normal coordinate that I introduced last time. The normal coordinate, right? So in this case, the normal coordinate u1 is given by x1 minus x2 divided by 2. And then this u2 is given by this x1 plus x2 divided by 2. Right? So then this u1 basically represents, right? So the amplitude of the one of the normal mode, right? So and then the u2 is the amplitude of the other normal mode. So then you can see that from here. So the u1 and u2, right? So they themselves, they don't change as a function of time, right? So the amplitude, the amplitude, u1 and the amplitude of this u2, they don't change as a function of time. Okay. So, and one thing I want to mention here is that you might have learned about waves, right? So for waves, you know that there are also many different modes, right? So if you have two fixed wall with a string, right? So you learn about standing wave before, right? So if you have this one, you know what are the modes that you have would be something like this, right? So you could either have, this is one of the mode, right? So and then this is the other mode, right? So this is the third mode and so on, right? So and you know that well, I'm not sure if you have really learned that concept already or not, but in fact, if you have this string, right? So if you make any arbitrary shape, okay, so for this string, right? So you know that it can always be decomposed into a superposition of different modes. Okay. So, and the idea, so it's the same as what we have here. Okay. So here we don't have a continuous string, right? So we have two particles, right? So, but just imagine the following, right? So imagine that we have a coupled oscillator, right? So with many mass. Okay, so like this, many mass. and then connected with many springs, right? So like n masses, right? So and then n+1 springs, and this system, right? So what you could imagine that you would have again normal mode, right? So if you have n particles, you will have n normal mode. Okay. So and if you really try to imagine that you take n to bigger and bigger, okay, tends to infinity. Okay, so the behavior of this one will tends to the behavior of this continuous string. Okay, so I'll talk about this one specifically in the later part of this chapter. Okay, but that's really is the idea. Okay, so any oscillations, okay, so can be written, expressed as a superposition, okay, so of different normal mode of your system. Okay, and then basically there won't be any the different modes won't be affecting each other. Okay, so that is to say, right, so as a function of time, right, so after you wait, and then you look at the system again, right, so you will still be able to tell me like this system is the superposition of the same two modes. Okay, and then the relative, let me put it this way, the relative strength of the two modes, okay, so they won't change as a function of time. Okay, so again, I'll get back to this n particle system later. Okay. Okay, so now here I want you to try one exercise. Okay, so it is again a couple oscillator problem, but the setting is, well, it's different from what we had. Okay, so now what we have, instead of 3 springs with 2 masses, what I have is that 2 simple pendulums connected by 1 spring. Okay, so I want you to try to write down the equation of motion. Okay, so you can start with the Lagrangian. Okay, try to start with the Lagrangian. Actually, you try to start with the Lagrangian, and then use, okay, the hints is that use this theta 1 and this theta 2. Okay, so to be the generalized coordinate. Okay. Write down the Lagrangian first. And here again, we are making the approximation where the 2 angles are small. Okay, so meaning that you have some approximation that you'll be using. Okay, and also because of the fact that these 2 displacements are small. Okay, so and just so this graph would be this graph is correct. Okay, so but this picture is correct, but I want you to imagine that these 2 displacements are very small. Okay, such that you could basically assume that the spring is still kind of in a horizontal position. Okay, roughly. Okay, so first thing would be simple, right? So the kinetic energy would be the kinetic energy of this one plus the kinetic energy of this one. Right. So if I use the theta 1 and theta 2 as the generalized coordinate, right? So how do I express the velocity of this one? Right. So you know that in this theta, this polar coordinate, right? So if you consider this theta as your polar angle, right? So you may still remember that the kinetic energy would be 1/2 m r dot square plus r theta dot square. Right. So, but however, the r dot is 0 because r is always equal to b. Right. So that therefore, the terms that we have is just 1/2 m b theta dot square, right? B theta dot 1 square. So that's the kinetic energy for the first one. And the kinetic energy for the other one, of course, just 1/2 m b theta 2 dot square. Right. So that's it for the kinetic energy. So now the potential energy of the system. Right. So we have two kinds of potential energy this time, right? So the of course, the elastic potential energy due to the spring, and also we cannot ignore the gravitational potential energy, right? So because individually, right? So gravitational force itself is the source that provides the restoring force for the pendulum, right? So now let me, if I draw again, let me draw another pendulum over here. Right, so you should have already done it multiple times, but so let's say at the lowest level, right? So u is 0, right? And then so then this height, what is this height over here? So this is theta. Right, so that then this height over here would be this is b times 1 minus cosine theta. Right, so this is the height that we want. Right, so this is the height that we want. So therefore, the potential energy would be mg b times 1 minus cosine theta 1 plus mgb times 1 minus cosine theta 2. Right, so that's the gravitational part. Okay, so now that's the one that we need to be a bit careful is the part for the elastic potential energy. Okay. So initially, right? So okay, so one assumption that I made, and you probably know it already, is that when both masses are at the equilibrium position, right? So the spring is not stretched or compressed. So that's the assumption that we make. Okay. So at the equilibrium position, this is just the natural length. Okay. So now, then I want to know when the two particles are like this, what would be the stretching or compression of this spring, right? So then what I really need is to know this distance and this distance. Right. So this is x2 and this is x1. Okay. So the extension or how much the spring is stretched would be given by this x2 minus x1. Right. So because if these two are the same, that means that the distance between this and this is still the same as what we have at the equilibrium position, right? So then that will be no stretching. So what it matters is the x2 minus x1. Okay. So here, as I said, right, so we are really considering small displacement. Okay, so such that you just imagine that this spring is roughly horizontal. Right, so that's why I can just simply say that the extension is given by x2 minus x1. Okay. So and what is x2 and what is x1? Right, x2 is just b sine theta 2. Right, so x1 is just b sine theta 1. Right, so therefore the elastic part, the elastic potential part is the 1/2 the kappa times x2 minus x1, right? So it's b sine theta 2 minus b sine theta 1 squared. Right, again, it doesn't matter whether x2 is really greater than x1, as in this picture. Right, so I have x1 greater than x2, this expression for the potential energy still works because I have the square. Okay, so then what's next? Time to make some approximation, right? So now the angle is small, so then I'm going to apply the following assumption, right? So sine theta is approximately equals to theta. Cosine theta is approximately equals to 1 minus theta square divided by 2. So then the potential energy is roughly equals to mgb. Right, so this 1 minus cosine theta 1 is roughly equals to theta 1 squared divided by 2. Right, similarly, this one is roughly equals to theta 2 squared divided by 2. Okay. And then for the elastic potential part, right? So the sine theta becomes theta, right? So I'll just write kappa, and let me take out the b first. Kappa b square theta 2 minus theta 1 squared. So then that's for the Lagrangian, right? And of course, the next step is to use the Lagrange equation, right? So use the Lagrange equation for the theta 1 and theta 2, right? So then you get two equations of motion, right? So the two equations of motion would be right. Just apply the Lagrange equation. Okay. And the other one, okay, so notice the difference here. So this one is theta 1 minus theta 2, and this one is theta 2 minus theta 1. Okay. So because why is there a difference? Because when you do this, so what you have is 2 times theta 2 minus theta 1. And you pick up a minus sign over here. Right, so if you do the partial derivative for this term with respect to theta 1. You pick up a minus sign. Okay, so however, if you do the derivative with respect to theta 2, then you don't pick up a minus sign, right? So then that's why this one and this one are off by a minus sign. Okay, so then system of equations are ready. Of course, the next step, is the matrix form, right? So first of all, you can see that there's some factors that can be canceled out, right? So the B let me get one more page. So in matrix form, I'll just write it. Okay. So then the next steps would be just standards, right? So finding the eigenvalues and eigenvectors for this matrix, right? So eigenvalues. Right, this determinant would be equals to, right, so this whole thing square minus kappa divided by m square. And that has to be, and this is just equals to, right? So a square minus b square is just a plus b times a minus b, right? So then this can be written as this, and it has to be equal to 0. So then therefore, lambda would be either just g divided by b or g divided by b plus 2 kappa divided by m. Right, so that therefore the eigenfrequencies are, right, so the omega 1 is just square root of g divided by b, and omega 2 is square root of g divided by b plus 2 kappa divided by m. Okay. Okay, so you can try to verify that the eigenvectors for the two eigenvalues are 1, 1 and 1 minus 1 respectively. Okay. So again, these two are not surprising, right? So because again, if you just look at the system, you might already feel that how the two normal modes look like, right? So the first one, again, would be that the two pendulums oscillate in phase, right? So and with the exact same amplitude, right? So in that case, if they oscillate together in phase, then the spring is basically useless, right? So they oscillated together like this. So the spring will never be stretched or compressed, and then the whole behavior, it just looks like the two individual pendulum oscillating, right? And therefore, the frequency would be just given by the frequency of a simple pendulum, right? Square root of g divided by b. So then this is of course again the symmetric mode, and the other one, the anti-symmetric mode, right? Is that the two particles oscillate out of phase, right? Same amplitude, but there's a pi phase shift. Right? So then in that case, the spring will be stretched and compressed, right? And therefore, we do have some contribution from the springs, right? So therefore, we do have a different eigenfrequency for this mode. Okay, so now let's try to consider more complicated situations. Okay, but you could see that the method itself is exactly the same. Okay, so is that instead of just 2 masses, 3 springs, I have 3 masses, 4 springs over here. Right, just adding 1 more unit. So, and now if I want to solve this system, right? So again, I just need to write down the Lagrangian first, right? So this time I will have 3 variables, of course, by x1, x2, and x3. And the 3 terms for the kinetic energy for the 3 particles, right? So, and then for the potential energy, right? So this time I have 4 terms because I have 4 springs, right? So this one for this spring, right? So this one for this spring, and then this one for this spring, and then this one for this one. So, and after that, right? So you just again apply the Lagrange equation, and this time you find 3 equations of motion, right? Of course. And what we do next is the same, right? So it's just that we make this in the matrix form, and what you get would be something like this. So this is the matrix you get. So now, as I said, right? So the steps will be the same, right? So is that you just find the eigenvalue for this matrix, and if you do that, right? So you will have to deal with this 3x3 determinant, right? So it's a bit more complicated, but here it would be what you get. Okay, so there are 3 eigenvalues, and that means there are 3 eigenfrequencies. And then you also find the corresponding 3 eigenvectors. So then that means the general solution, right? So would be a superposition or a linear combination of 3 normal modes, right? So instead of just 2 normal modes, right? But everything is just expected, right? So really that well, the step of the math would be more complicated, but the idea is still just rather simple and the same as what we had before. So now let's try to understand. Okay, so intuitively the behavior of the 3 modes. Okay, so I have you can see that I have the 3 eigenfrequencies. So this one is the lowest, this one is in the middle, and this one is in the highest. Okay. So let's try to draw some pictures for them one by one. Okay. So let me start with the simple case. That is for omega equals square root of 2k divided by m. This is the eigenvector. Okay. So can you see what's going on? Right. So in this system, right. So 1, 0, -1. So that means that in this case, the mass in the middle is not moving at all. Right. It just always fixed here. And then the one on the left and the one on the right are doing the out of phase oscillation with the same amplitude. Right. So that is this one when it moves like this, and then this one moves like this. And then after some time, right, so this one will become here, and then this one will be here. Okay, so now looking at this picture, you might understand why we have this square root of 2k divided by m, right? So because if this one is not moving, so that means you can just consider this one is another fixed wall, right? So then you can just look at the two systems separately, right? So if I just look at the system on the left, then all you see is one mass connected to two springs on both sides, right? So and that is why you have this square root of 2k divided by m. Okay. So now for the other two modes, okay, so things will be a bit more complicated, right? So but let's see. So it's 1 square root of 2 and 1. So this time they are all oscillating in phase, right? So but just with different amplitude. Right, so that is when this one moves to the right by 1 unit, and this one move to this one move to the right by also 1 unit, then the one in the middle will move to the right by something bigger. Will move by a square root of 2 units, right? So, and then for the last one, where I have this 1 square root of 2 and 1, this time these two are the same like this, but then the middle one will be moving to the left this time, right, like this. Okay, so you can see that we have different eigenfrequency for different modes. Okay, and the one that has the higher frequency, okay, usually will be the one that involves more spring. Right? So what I really means is that if I go back to look at the case of the two particles, right? So this is the anti-symmetric mode with the higher frequency. This is symmetric mode with the lower frequency. And for this one, you can see that all three springs are playing their role in their motion, right? So stretch, compress, compress. Right. So, but then this one of the spring is not really doing anything, right? So this one is never stretch or compress, and this one has a lower frequency. So then, roughly speaking, right? So you could really see that this one, right? So will contain more elastic potential energy than this one because all the springs are playing their role, right? And the mode with the higher frequency would be the mode that with the higher energy. Okay. So then similar things happens in this case. Okay. Sorry. In this case, okay. So of course, in this case, all the springs are really playing their role. Because all of them will be either stretched or compressed. But the amount of compression and extension, okay, so for different cases are different. Okay. So for example, you can see that in this case, the amount of compression or stretching would be small, okay, compared to this one. Okay. So because in this case, right, so all the springs are really kind of moving to one side. Okay, and therefore you will be creating not really that much stretching or compression for this spring and this spring. However, for this one, because of the fact that these two are moving to the right, but then this one is moving to the left, right? So therefore, you create much more significant stretching or compression for this spring and this spring, and that lead to a higher frequency or high energy for the mode. Okay, so before we move on to the next part of the chapter, here again I have one question that I want you to think about. Okay, so actually we should take a break. So you can think about it during the break time. Okay, so we'll come back at 10:30. Okay, so the question I have for you is the following. Okay, so here I'm again just considering the example that we have done is the 3 springs tooth mask. However, this time I'm going to change the setting a little bit. Okay, is that I no longer have this condition. So, right, so initially, so what we are considering is that none of the springs are stretched when I set these things up. Right. So now imagine the following. So when I set these things up, okay, so they are already stretched a little bit. So that is to say, this length is already L0, which is the natural length plus something. Okay, so this one also L0 plus something. And the middle one, let me call this L0 plus also plus something. Okay. So when I set this up, so they are stretched already, but the whole thing is in equilibrium. Right? So you can imagine that, right? Because if I stretch this one and this one, if the stretching are right, then the total amount of force acting on this would be 0. Right. So similar for this one, if the stretching and this and the stretching of this one, the ratios are right, then this net force acting on this particle is again 0. Okay. So okay, so the whole thing still at equilibrium. And then I want you to consider with this system how the Lagrangian would change, how the equation of motion of change, and most importantly, whether the eigenfrequency, the oscillation frequency, would change or not. So that's I want you to try to think of. Okay, so we will come back at 10:30. Okay. So when you think about the problem that I just posted, you can take one step backward and go back to think about something a bit more simple, and that I talked about previously is that remember if I just have one spring, one mass, right? So and for this one I have just square root of k divided by m, right? So and if I think of one spring, one mass with a constant force on one side, and at the end the frequency is still the same. Okay. So remember this simple situation over here. And then next you could think of the following, right? So that I have, right? So 2 spring, 1 mass. Right, so remember that if I don't have stretching on both sides, let's say, then what you have would be square root of 2k divided by m. Right, so then let's say you build another system, right? So with stretching like this, right? So and think about what's going on, right? So will you still get square root of 2k divided by m. Right, so in this case, if you try to displace the mass to one side by an amount x, right, so that the force that you get would be from the left, the force that you get would be minus kx, right, and then from the spring on the right, you get another minus kx, right. So, but now in this case, right, so what happened is that if you are going to displace this mass to one side like this, right, so this time what I have is the following, right? So in this case over here, I have this to be L naught, and this one also to be L naught, right? So but this time this one would be L naught plus epsilon, and this one is also L naught plus epsilon, right? And therefore, right, so the spring force, okay, so from the left, what would you have is minus, right, so this is the x, right, so if the mass is right over here at the red position, the total stretching of this spring on the left would be epsilon plus x, right, it would be minus k x plus epsilon. But what about the other one? So the spring on the right, so what about the spring on the right? Right, so then it would be, it might still be stretched actually, right? So because original is stretched by epsilon, right? So now you move it to the right by an amount x, right? So then the stretching would be epsilon minus x in that case, right? So then the force that you have would be k times epsilon minus x. Right. So, but what about you tell me that no, actually this x is already greater than epsilon, right? So that means that in this case, this spring is already compressed. What about that? How do I think about that? But that's okay, because in that case, I will know that this spring is compressed and how much it is compressed. It is compressed, the amount of compression this time would be x minus epsilon. But because of the fact that this is actually compressed, then the force is due to compression, not stretching. If it is due to stretching, we know that the force by the right spring is to the right. So that's why I don't have a minus sign here. But now, because if you tell me this is compression, then the force will be to the left. So that means that the force will be minus k, x minus epsilon, which is the same as k times epsilon minus x. Right. So in either case, the same expression would work. Okay. So therefore, right, so the total force, right, so the total force would be minus k x plus epsilon, right, so plus k epsilon minus x, and this epsilon term exactly cancel. Again, you have these two minus 2kx. And that will be the same as this one. So therefore, same kind of restoring force, then same kind of oscillation frequency. Okay, so then let's actually get to the problem that I was trying to consider. Right, so here, right, so if you try to actually modify the Lagrangian, right, so what you would do, right, so of course the kinetic term won't be modified. And now, instead of having this kx1 square, right, so then here this x1 has to be replaced by x1 plus epsilon, right? So because I'm talking about the total, the amount of stretching in this spring is not just x1, it would be x1 plus the original stretching epsilon. So this one becomes x1 plus epsilon, right? So what about this one? This x2. So this x2, now you can see that the compression is not just x2, right? But it has to be x2 minus epsilon. So this x2 would become x2 minus epsilon. Because originally it stretched a little bit. Now you compress it by an amount x2, then that's why the net compression will be x2 minus epsilon. So what about the middle one? So what is the amount of stretching that we have in the middle spring? Right. So that would be x2 minus x1 plus the original stretching epsilon prime. Right. So this one would become x2 minus x1 plus epsilon prime. So this is how you would modify the Lagrangian if you have the stretching already initially. Then how it affects the equation of motion, right? So that means that, again, as I said, right, so this x1 becomes x1 minus plus epsilon, right? So this one becomes x2 minus x1 plus epsilon prime. And this one also. Epsilon prime. And then this one would be x2 epsilon, right? Okay, so then what does that really mean? That means that your equation of motion will have some additional constant terms, right? So you have this k epsilon, this k12 epsilon prime, this k epsilon, and this k12 epsilon prime. But that's all, right? So then if I'm going to just write the constant term separately, if I just write the constant term separately behind, then what you have would be the following, right? So then this whole thing would have this minus k epsilon plus k12 epsilon prime. And similarly, for this one, right? So then you have the constant term. So then would they affect the eigenfrequency? Right. So if you just write, again, try to write the whole thing as matrix form, right? So what would you will have is that I will have this whole thing still plus the constant term that I just showed, right? So just constant. Okay. So then you can really try to do all the details, right? So just try to think a bit about whether that would affect the process of diagonalization, right? So, and obviously it doesn't, right? But because of that, the eigenfrequency of this system won't be affected by adding the constant term. And at the end, you get the same eigenfrequency. Okay, so and that's the last thing I want to talk about for this part 1 of the chapter. Okay, so let's get to part 2. So for part 2, what we are going to talk about are basically more different kinds of examples. Okay, so the idea of normal modes will still be used. Okay, so by going to just let you see some other kind of couple oscillators in other physical systems. Okay, so not just masses with springs. Okay. So the first example that I'm going to show you actually is not really a mechanical system. Okay, so well, this is a mechanics course, but here, right? So I want to show you that we have the oscillator behavior, right? So in circuits. So I believe that you have learned, you have the basic knowledge of this elementary circuit element, like capacitor and inductor, right? So I believe that you don't have much problem understanding this. Right? So here, what do I have? So I have a circuit consists of an inductor, like a coil, right? So and a capacitor. Okay. So and now what happened is that I initially just imagine that this is an open circuit, and then I charge up this capacitor. Okay, so such that you can see right here, some amount of positive charge is stored, right? So on the left plate, and then the same amount but negative charge are stored on the other plate, right? So and in this configuration, well, I'll say that there is amount Q stored in this capacitor. And then once you just basically close the circuit like this, and then so this one is just connected to this inductor, what happens is that it will discharge, right? So that is the charge will flow. And now there would be a current flowing through this coil. Right? And now this is not a constant current, it would be a changing current. And because of a changing current flowing through a coil, and there would be a back EMF that is induced, right? So it's trying to oppose the change in current, right? And now, what we want to study is how the charge or the current, okay, as a function of time would behave. So, and here, notice the convention I used. Okay, so I have this current equals to minus dq dt. Okay, so because here I am just defining current. Okay, so as the amount of charge flowing out of the capacitor per unit time. Okay, so I equals to minus dq dt. So now let's set up the equations, okay, for this circuit, right? So by Kirchhoff laws, right? So then what we have is the following, right? So the Q divided by C, right? So that would be the EMF due to the charge capacitor, right? And then the L times dIdt, right? So this, again, I believe you have learned this in your E&M course, is the back EMF induced by the back EMF given by the coil. Right? So then this is the really simple equation that I can write down for this circuit. And now, if I just take the derivative one more time on both sides, right? So this becomes the second derivative, and this I have this dq dt on the right hand side, and remember that this dq dt is minus I, right? So then I have this one. So now if you look at this form, right? So it immediately reminds you of simple harmonic oscillator, right? So because of simple harmonic oscillator as the equation of this form, right? So then of course it's not a mechanical system, but you could really see that how this is an electrical analog for the simple harmonic oscillator. But anyway, so you know that in this case, right? So what is the behavior of the current? Right. So the behavior of the current would be a sinusoidal function, right? So and the frequency of that sinusoidal function will be given by this prefactor, right? So the current oscillates as a function of time, and of course, in this case, so let me draw a picture. Right, so I as a function of time will look something like this. Right, so given that the initial condition is that this capacitor is charged up but no current, right? So then this would be our result. Right, so with this frequency. Okay, so now this is the simple oscillator, simple harmonic oscillator. But what we really want to talk about, of course, is coupled harmonic oscillator. So then we'll have this circuit. Okay, so this circuit might be something that you have not really seen before, right? So, but let's try to analyze this. So again, all you need to know is the Kirchhoff law. Okay. So see the setting here. I have this 3 capacitors, right? So kind of in parallel, right? And then I have 2 inductors over here. Okay. So and then I define 3 quantities. Okay, so the I1, so which is the current flowing through the left half of the loop, and then I2, the current flowing through the right half of the loop. But you know that I1 may not be equal to I2 because I have an additional path over here. Okay. But what we can say at least is that this I2 would be equal to I1 plus I12. Okay. And that's why this I12 would be equal to I2 minus I1. Okay. And also, again, notice that how I set up the convention for the current. Again, I have this charge, positive charge here, positive charge here, positive charge here, negative, negative, negative. And the current would be, as you can see from my arrows, is that it's talking about the charge flowing out of this capacitor in this direction per unit time. Okay. Okay, so now let's again use the Kirchhoff law to set up the equation for the circuit. Okay. So the first is that I'm going to just consider this loop, right? So I can apply Kirchhoff laws, right? So for one of the subregion of the circuit, right? So as long as I consider a complete loop here, right? So then if I just consider this left loop in blue color, right? So then I will have this equation over here, right? So that this Q1 divided by C would be due to this component, right? So this L di1 dt would be due to this component, and then this Q12 divided by C12 due to this capacitor, right? So three components in one loop. Okay. So now similarly, if I consider the right loop this time, so if I consider this one, the one in red, then I have this equation, right? So again, three components. The first term from this C12, right? So the second term from the inductor, the third term due to the capacitor on the right. So now I have these two equations over here. And then if I'm going to take the derivative, right, with respect to time, then these are the two equations that I got. And also, I've already used this relation over here. Okay, so let me just try to rearrange the terms to make it look more clean. Then you get this. So then this form really, again, looks exactly what we had for the coupled mass spring system, right? So second order derivative on the right-hand side, on the left-hand side, and then the two variables on the right-hand side. And if you now make it in the matrix form, okay, so something like this. So now you can follow the same mathematical procedure, and then you find the eigenvalues and eigenvectors. Okay, so like this. Okay, so now again, how do we try to have some picture on the two normal modes, right? So can you try to maybe take just 1 minute to try to draw a diagram on how the currents are flowing? Okay, so for these two cases. So this one and this one, right? So when I have a positive number, right? So that means that it's anti-clockwise direction, right? So you can see my convention over here. Right? So when I have a negative number, so that means it's I'm sorry. When I have the positive number, it's clockwise, right? So negative number anti-clockwise. Right, so that is to say, if I am considering the first case over here, so what I have is something like the following. So, of course, okay, we understand that the direction of the current will change sinusoidally, right? So, but at a particular moment, right? So if I consider this I1 to take this negative value, then that means that I'm having a current like this. Right. And then for the other loop, right, so on the right. So, and it will be something like this. So this is the first mode, right? And you could see that what we have over in the middle what would it be? Because the amount of the current will be the same. Okay, so in the two loops. So here I have 2 times the current. So right, so if this is I, right, so there will be 2I over here. This will also be I, but it's just in the opposite direction. Okay. So this is what we have for this mode over here. And what about this one? So this one is interesting here. So because now in this case, I would have the both direction to be the same, right? So that is, let me just try to change. Right, so this time I just need to reverse the direction of the arrows like this, right? And here you can see that now I have this I going up, but also the other flow I going down. Right, so actually the currents in the middle part would be 0. Right, so no current here. So if there's no current over here, so basically I can just ignore this part of the circuit, right? And just draw a big loop like this, right? Completely ignoring this one. And this one, right, so would be, what do we have? So the circuit diagram for this one would be just like this, right? So I have the 2 inductor in parallel in series, and then I have also 2 capacitor in series like this, right? So equivalently, right, the circuit looks like this, right? This L, L, C, and C. So if I have 2 inductors in series, you know that it is just equivalently is a inductor with double of the inductance, right? And now if I have these 2 capacitors in series, then it's just like having 1 capacitor, but with half of the capacitance. So in the simple harmonic oscillator case, we know that omega is square root of 1 divided by LC. Right. So, and now in this case, the omega would be square root of 1 divided by 2L times C divided by 2. And that would be the same as 1 divided by LC. So that's what we have over here. Okay. Okay, if you are really not really familiar with circuits, that's fine. Okay, it's okay for you to kind of skip this example over here. Okay. So now let's look at something that we have actually seen in the last chapter. Remember this one? Okay, the pendulum with a movable support. Okay. So I'm going to show you that how this one behaves like the earliest example that we talk about. Remember, we have this example, just 2 masses and 1 spring. I'm going to show you that how this one is similar to this one. Okay. So in this case, so I'm not going to kind of tell you in details about the Lagrangian one more time because we done it already, right? So is that it's just the Lagrangian is just written here. Okay, so kinetic energy for the big mass over here, this whole thing, the kinetic energy for this small mass over here, right? So and then the potential energy for the small mass. Okay, so this is something that we have seen already. Okay, so I want to kind of emphasize that this is like a harmonic oscillator, right? So what I'm going to do, let me just rearrange the term first. Here I did nothing, but just rearrange some terms, right? So I just put all the x dot terms up front, right? So the theta dot term in the middle, right? So the potential energy is still here. Okay. And then I'm going to make approximation one more time. Okay. So the approximation that I'm going to make again is for the cosine theta, right? So the cosine theta approximately equals to 1 minus theta squared divided by 2. Right? So now I want you to focus on this term and this term. Right? So for this one, let me actually. So this one would be just MGL 1 minus theta squared divided by 2. Okay. And this one need to be a bit more careful actually. So I have this 2L x dot theta dot times 1 minus theta squared divided by 2. Okay. And that would be 2L x dot theta dot minus x dot theta dot times theta squared divided by 2. So nothing wrong is here, but what I'm going to do next is to actually further ignore this term. So this is one more approximation that I made. Okay. So why? Okay, so because you can see that this is a term that contains a variable, okay, multiplied by another variables. So there are 4 variables multiplied together. Not really 4 variables multiplied together, but just the variables because I only have 2 variables in strictly speaking, but it would be a 4th order term. I should put it this way. It is a 4th order term. So, and because of the fact that I'm going to consider an approximation that the oscillation is small. Okay, so if the oscillation is small, that means theta is small, x is small, x dot is small, theta dot is small, and all that. Okay, so then because if you see this term, that means I have this small number multiplied 4 times, and this would be, of course, much smaller than this term. Right. So this is x dot theta dot. It's just a 2nd order term, so I keep this. Right. So you can see here. This is a 2nd order term because x dot times x dot. Right. So this is a 2nd order term. So theta dot times theta dot. So these are the terms that I want. Okay. So this is x dot theta dot, also 2nd order term. So I keep. Right. So this is theta dot square. I also keep. But this is a 4th order term, and that would be much smaller compared to the 2nd order term. Okay, so that's why I dropped this one. And therefore, after that, I would only have an expression that looks like this. Okay. So, and now, at this point, right, so I'm going to, again, apply the Lagrange equation. Okay. So if I'm going to apply the Lagrange equation for the theta variable and the x variable, and these are the 2 equations I got. Okay. So now, let me try to make it in the matrix form. Right. So this time, it looks something like this. Looks something like this. So this is not really the same form as what we are familiar with, right? So what we had previously for the coupled oscillator would be a form that looks like this, right? I don't have any matrix on the left-hand side. I only have a matrix on the right-hand side. So here I have matrix on the left-hand side, also a matrix on the right-hand side. Okay, but you can just also put this to the right-hand side, right? So by multiplying an inverse of this matrix for the two sides of the equation. Right. So if you do that, then I will have a system that looks like this. Right. So then now only the right-hand side has a matrix. Okay, so now well, I have two zeros in this matrix, but anyway, I can still try to find the eigenvalues and eigenvectors. Okay, if you actually try to do that, you'll find that the two eigenvalues are this big M plus small m divided by big M times G divided by L, and 0. So, and actually, this is something that I've talked about in chapter 2 already. Okay, so but now in this, using this eigenvalues, eigenvectors formulation, okay, so we obtain the same result one more time. Okay. So now, what are the physical pictures? Okay, so for these two modes, right? So this one, okay, so the first one, of course, would be a small oscillation that looks like this. Was I have a mass on top, another hanging, and then the oscillation will look like this, right? So this one is, when this one is moving to the left, right? So this one is swinging to the right, right? So when this one is to the right, right? So this one is to the left, right? So you know how it works, right? So like sometime later, maybe the mass is right over here, and then the pendulum is right over there, like this. Okay, what about the other one? So the other one, you see 0. So remember, the 0 frequency is not really an oscillation. Okay, but you could really imagine what happens is that the whole system is moving at a constant velocity. Okay, so it's just like this. Not an oscillation. But just imagine that the whole system is put, maybe it's put on a car, which is moving at a constant velocity. So this is what happens. So then, remember when we consider this one spring two mass system, right? So we got something just like this, right? So the oscillation would be the two masses, right? So oscillating in phase, right? So that would be the oscillation. And then also, right? So the whole thing can be moving together at a constant velocity, and that is not oscillation. Okay. So, and then the next one, again, it is an example that you have seen. Okay, so if you have attended the exercise class. Okay. So I think in that exercise class, you have tried to derive the Lagrangian for this so-called double pendulum. So what is double pendulum? So for a single pendulum, I just have this one massless rod and this one mass particle. For double pendulum, I attach another rod to this mass, and then at the end of that rod has another mass, right? So, and this point is free to rotate, right? So this rod is free to rotate about the first mass over here. And of course, this point is also, this is also another freely free period. Okay, so that's, this rod is also freely rotate about this point. Okay. Okay, so this is a double pendulum. Then now, in general, okay, so the double pendulum can be a very complicated problem if the amplitudes are large. Okay, So, but again, we are just going to consider small amplitude approximation. Okay. So, but anyway, so how do we set up the system, right? So again, I will first need to write down the Lagrangian of the system, right? So I'm not going to rederive the whole expressions for the Lagrangian, but just give you some quick reminder. Okay, so the kinetic energy first, right? So the kinetic energy of this one. So if you just have the single pendulum, you might find it convenient to use the theta as a coordinate. Right? So, but now if you consider the second mass, you will find that it's very difficult for you to directly just use this theta 1 and theta 2 to express the velocity of this m. So therefore, as an intermediate step, okay, so we'll also first consider the xy coordinate of the two masses, right? So like this point, the coordinate is at x1, y1. This one is at x2, y2. Okay. So one thing careful here is that here we pick the vertical axis to be x and the horizontal axis to be y. Okay. And also going down is positive. Okay. But anyway, if I have this x1, y1, x2, y2, then what you have for the kinetic energy would be 1/2 m x1 dot square plus y1 dot square plus x2 dot square plus y2 dot square. Right. So, but ultimately, we do want theta to be the variable. Okay. So therefore, we are going to express these four numbers in terms of the theta variable. Okay. So this should not be difficult to see that x1 is actually, so x1 is this, right? So x1 is actually L cosine theta 1, right? And then this y is L sine theta 1, right? And what about x2, right? So x2 would be this red distance plus this green distance, right? So therefore x2 would be x1 plus something. So that's x1 is L cosine theta 1 plus L cosine theta 2, right? So similarly, y2 would be L sine theta 1 plus L sine theta 2. Okay. Right, so with all that, you'll be able to just take the derivative, right? So you should be able to express all these derivatives in terms of theta 1, theta 2, theta 1 dot, and theta 2 dot. Okay. Okay, so what about the potential energy? Potential energy of this one would be minus mg x1. Okay, so now this one has to be careful. Why is it minus mg x1, but not just mg x? But because now we consider the downward direction to be the positive direction. Right, so that's why the potential energy is minus mg x1. And then the other one, so it's minus mg x2. So again, you just need to express this x1 and x2 in terms of theta. Okay. So then, if you do that, you'll be able to find that the Lagrangian is given by this first line over here. Okay. And now, after using the approximation that cosine theta 1 is equal to approximately equal to 1 minus theta square divided by 2. Okay, so you'll be able to get to this expression over here. Okay. So then Lagrange equation, right? So then the equation of motion looks like this. Again, matrix form, like this. So once again, you see that now I have a matrix on the left-hand side. But again, that doesn't matter, right? So you can always make it to the right-hand side just by multiplying an inverse, right? So then this is the form that we like, right? So after you get to this form, no need to worry, but just do the same procedure. Okay. So, and you will find that the eigenvalues and the eigenvectors are given here. So again, we can take a look at the picture, right? So for this one, so again, it's kind of an out of phase oscillation, right? So that is to say, when theta 1 is kind of negative, right? So then theta 2 would be positive with a bigger number. So then the normal mode looks something like this. Right, so when it is moving to that side, this is moving to this side. So what about the other one? So the other one would be an in-phase oscillation. Right, so when this is like this, the other is having a bigger angle. That's it. So same direction. So these are the two normal modes. Okay, of course, I'm exaggerating the angles. So as I said, this only works for small angles. And one thing interesting to notice is that, and I didn't really mention it much, I will next time, is about the orthogonality of the two eigenvectors. Remember when we talk about the mass spring system, right? So the eigenvectors are these two, right? So symmetric, anti-symmetric. So these two vectors are orthogonal, right? So if you take the dot product of these two, 0. But this one, if you take the dot product of this one and this one, non-zero. Okay. So one thing to take notice. Okay, so next time I will talk a little bit about more about the orthogonality of eigenvectors. Okay. Okay, so I think this is a good time to stop for today. Okay. So these examples, right, so are slightly different from what we have in the mass spring system. Okay. However, at the very least, right, so the important point for you, first of all, you must be familiar with the mass spring system. Okay, so know how the eigenvalues and eigenvectors work. Okay, so that's the most important part. Okay, okay, so then we'll continue next week.